years, but
Right.
so like, interesting.
Today, I'm like,
Okay, so I think everything's fine already. I'm sorry, the screen was kind of blurry, so there was no way they could see the page. The what? Sure.
I mean, I don't know if it will, so.
No, it was out of focus. That was but, okay, so a couple of things that we were talking about last class. We were talking about torques, and we were looking at torque as a way to describe any kind of rotational motion, and the same way that we use force to evaluate when something was moving in a straight line. Every time that something is going to be moving some kind of in a rotational way, either you have a ladder that is falling, or you have your arms that are going to be rotating, or someone that is running. Everything that is moving along a pivot point is a kind of rotation, and that can be described as a torque. And we look at this equation that basically the torque is the distance between the pivot point and where the force is times the perpendicular force. And we define that perpendicular force as the force that is perpendicular to that radial axis. Okay. So what I want to do today is just look at different kind of torque, and it's basically the torque caused by gravity. So if you imagine that you have your arm, and it's just your arm, nothing else. You are activating some muscles in your shoulder to keep your arm in that position. Okay. Otherwise, your arm will fall and it will rotate towards your leg. Okay. So there's a torque going down on this way, going clockwise, and is basically a torque that is being caused by the force of gravity. The mass of your arm is being pulled by gravity, and basically you have that force that is pulling you down. Now, the question is, how do we calculate that torque caused by gravity? So now, it's not such a simple problem. If instead of having an arm, we'll have like a little light rod, and at the end we have a mass. Well, if the pivot point is here, and all the mass is in one end, then we can apply the equation of torque the same way that we have seen it so far. But in the case of the arm, the mass is distributed along the whole length of the arm. So instead of having something like that, you have something that is more like a rectangle. And the mass that you have in this mass, you have it here. But now the radius, that distance to the pivot point, is not constant. Instead of just being in one location, it's all over this. So which one do we use? So there are different ways that we can calculate this. The one that is more complicated, that we're not going to use, but I'm going to explain it so you can get an idea, is that we divide this arm, or we divide this object in small little segments. And I'm going to divide the mass, or I'm going to divide the object in such a way that each one of these little segments have the same amount of mass. So I will have here M1, M2, M3, all the way to Mn. Okay, so I'm going to have n segments of my arm, and all of them are going to be exactly the same. So for each one of these segments, I'm going to have an R1, a distance. a distance from the center of this to my pivot point. So I'm going to have an R1, I'm going to have an R2, an R3, all the way to an Rn. And then to calculate the torque, well, it will be the R1 times M1 times gravity plus R2, M2 times gravity, all the way, blah, 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 to Rn and N times gravity. Okay, so then the problem is, okay, how many segments do I need to have in order to get a good answer? And the more segments you have, the more precise your result is going to be. But it also going to make your calculation longer. And the less segments that you have, you're going to be able to calculate that very easily, but it's going to have a lot of error. We usually do this as an integral, so you integrate along this section, and we need to do that if you have an irregular body or something that has a very complex geometry. But if you have something that has a very simple geometry, like a rectangle, or a triangle, or a sphere, or a circle, something, some simple geometric figure, what we're going to do instead is to use what's called the center of gravity. Okay, and the center of gravity is a location in space where the mass of the object is concentrated. Concentrate. Okay. So, for example, let's say that we have two masses connected by a simple rod, and so it's going to look something like this. So we have M1, and then we have M2, and we have a small rod connecting both of them. Okay. Now, let's say that somewhere around here, I put a pivot point, kind of like a balance. Okay, so you can imagine that M1 is trying to rotate in this direction, and M2 is trying to rotate the whole object in the opposite direction. So we're going to have a torque caused by M1, or we're going to have a torque caused by M2. But if I pick this point, this pivot point, if I pick it correctly, there's going to be one particular location in which the whole system is in balance. Yeah. So when the two torques caused by the two masses is equals to 0, it means that we have found our center of gravity. So the center of gravity is a point where all torques are canceled, or all torques cancel each other. So the net torque is 0. So basically there's no rotation. Okay, you can think of that center of gravity as the balance point. Okay, so what we need to find out is, okay, how do we find this center of gravity? And there are different ways that we can do it. I'm going to do it for this case, for the case of the two masses of different size, and we want to find out where is the center of gravity. So the first thing that I'm going to do is I'm going to set up a frame of reference. And in this case, I'm only going to be working with the x-axis. So I'm going to have my center of gravity. Sorry, I'm going to have my axis. And here, I'm going to have the position of x1. Here, I'm going to have the position of the center of gravity that I don't know. That's what I'm trying to find out. And here, I'm going to have x2, the position of mass number 2. And again, what I want to find out is what is that location in which all the torques are going to cancel. So I want to find out where tau 1 plus tau 2 is equal to 0. Okay, so tau 1, remember, is the distance between the pivot point and the force, or the force of the pull for M1. So R1 is going to be this distance over here. And R2 is going to be this distance over here. So R1 is going to be the position of the center of gravity, which I don't know which one is it, minus x1. Okay, and that times mass 1 times gravity. This one is rotating counterclockwise, so it's going to be positive. And then for tau 2, the distance R2 is going to be x2 minus the position of the center of gravity. So it's going to be x2 times m2g. Because this one is rotating the object clockwise, this is going to be negative. Okay, so far so good? Okay, so what I'm going to do now is I'm going to add the both of them together. So I'm going to do it here. Here, just this is just algebra. If I'm going too fast or if there's a step that it doesn't make sense, just let me know. The same for the people on the chat. If I'm going too fast, just interrupt me and I can repeat. So what I'm going to do now is I'm just going to expand these factors over here. So here I'm going to have x cg m1g minus x1 g minus x2 g plus. Okay. I'm gonna let you copy this. Okay. Okay, notice how I have gravity, like a common term in all elements. So I can divide the whole equations by g on both sides of the equation. So I can cancel all these g's. And 0 over g is going to be 0, so it doesn't affect the right side. So basically, I got rid of the gravity. Now, what I'm going to do now, I need to solve for the center of gravity. So all the elements that have this term, x sub cg, I'm going to leave it on the left side, and everything else, I'm going to put it on the right side. So on the left side, I'm going to have xg m1 plus x sub cg m2. And then I'm going to pass these two on the right side, and then I'm going to have x1 m1 plus x2 m2. Okay, now I can factor out the x cg on the left side. So I'm going to have x sub cg m1 plus m2. And then I can divide quantity m1 plus m2. So okay, and that will be the location of the center of gravity. So again, if I were to put a pivot at that point, all the torque will be 0, and basically the system will be balanced. Yes, Ria?
So where did gravity go again?
So gravity, like here in this equation over here, oops. You see how gravity is a common factor in all of them? Mm-hmm. So that means that you can divide both sides of the equation, the left side and the right side, by you divide by g. And on the left side, they're going to cancel. And on the right side, you have 0 over g, which that's going to be 0. So it's going to cancel. Now, let's say we are working with two masses. But let's say that instead of two masses, you have 3 masses or 4 masses all along the x-axis. So you will have to do the same thing, the same steps, which can be very complicated. But at the end, you end up with an equation that's very similar to this. So if you have more than 2 masses, you're going to have x1 m1 plus x2 m2 plus blah 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 xn mn, and then you divide by the individual masses. Okay, if you have an object that is in 2 dimensions, like something that will look like this. So you can imagine that this is someone that is sitting. So this will be the mass of the head, the mass of the torso, and the mass of the legs, or the mass of the legs. And you want to find out what is the center of mass of someone in this position. So you have an x and a y direction. So in the x direction will be this equation over here, and in the y direction, it's exactly the same. You just replace all the x components for y components. Okay. Yes.
In your top equation, you have the xcgm1 plus xcgm2, but then when you got down to the second one, you only have one xcg. Does the other one just drop out, or they just combine?
Here, what I'm doing is I'm factoring out this.
Okay.
So if you expand this equation, you end up with this over here.
Okay.
So I'm just saying, okay, I have xcg equal common to the two elements. So I'm gonna have this, and then I have m1, and then I need to add the other m2.
Okay.
Yeah.
Gotcha.
Okay. Makes sense? Now, this helps, especially if you have like all the masses like in little points. Uh, and notice, for example, that in this case that I have here, the center of gravity in the x direction is going to be somewhere around here. And the center of gravity in the y direction is going to be somewhere around here. So in this case, the center of gravity is going to be somewhere outside the object. Okay, and that's very common, or it's not unusual to have the center of gravity outside the object. It's something that you will expect. Uh, have you seen on the Olympic Games the high jump that they do? Not the pole vault, but the high jump that they do like a really weird arc with their body. So. Uh, one of the reason, uh, one of the reasons that they do that, and I'm exaggerating here. So you see something like this. Now, if you have a person standing up, our center of gravity is usually somewhere around our belly button. That's usually where it is. Depending on the proportion of your legs with respect of your torso, it may be below or above your belly button, but it's somewhere around there. Babies, because they have like a huge head compared to their body, their belly, the center of gravity is actually very close to the chest, and that's one of the reasons that they have so trouble walking, because they just bounce their head a little bit and then they just fell. For us, it's somewhere around here, so very close to the belly button. Now, one of the cool things about moving your body is that, or one of the things that happen is that you move your center of gravity as you move your body. So when you do an arc, or when you are flipping, or you are running, your center of gravity is going to change. And sometimes the center of gravity can be outside your body. So when you have someone doing an arc, because they're doing a high jump, the center of gravity is actually somewhere below that person. And one of the reasons that matters is that if this is lower, it's going to use less energy to jump than if it were above that person. So it's a technique that it's a little bit more efficient, just because with less amount of energy, they can jump a little bit higher. So that's one of the reasons. Okay. The location of the center of gravity, it also matters in terms of stability and equilibrium. That's something that we're going to be talking about in the next couple of days. But the relationship between the pivot point and the center of gravity can define if an object is stable or not. So imagine that you have a pendulum, and this is just a very simple case. So you have a pendulum. This is the ceiling. You have your pivot point, that is the anchor point, and you have a pendulum. So you have a big mass connected by a rope. And this pendulum is going to be oscillating back and forth. And if you let it oscillate for a long time, it eventually going to come to a stop. And that position at which stop is basically their equilibrium point. It's a stable position. And that one is going to be, you have the pivot point, and the mass, the center of gravity, is going to be exactly below the pivot point. And this is a very stable position. The other case is the opposite. You have a pivot point, and then you have the center of gravity exactly above. You can find an equilibrium point here, but if this mass moves just a little bit, it's going to fall. So this is an unstable position. Now, think about how we humans walk, or how do we stand. The pivot point of us while we're standing up or while we are walking, our pivot point are our feet. And our center of gravity is above that pivot point. So we just naturally, we have an unstable position. And you can see this if you try to stand still, completely stand still, it's really, really hard. You're always going to be moving a little bit. You're gonna be, your legs are going to be twitching. Your shoulders are going to be moving. You're going to be moving something on your body. It's more obvious if you are on tippy toes. Is you are constantly moving to make sure that your center of gravity is exactly above your pivot point. Same thing happened with babies. That's why they fall all the time. They are unstable. They have no idea how to control their body, and their noggin is so big that if they just move it a little bit, they just fall. And if you see them running, if they see you walking and they open their arms and it seems that they're gonna land on their face every single step. It's just they cannot they are a very unstable position. Have you seen people walking on wires? So there are different ways, but a very common way is that you are walking on a wire and they have a big, huge pole. And that pole is not straight. That pole makes a big arc. Now, you are walking, so the pivot point is going to be somewhere around here. And what the pole does is move your center of gravity below you. And actually, the idea is that they will move the center of gravity below the wire. So what you have here is basically a pivot point with the center mass below you. So this is a stable position. What is impressive is when people walk on wires and they don't have the pole. That's weird. Okay. We're going to be talking about a little bit more about stability and balance. But I just wanted to give you, like, this is one of the reasons that we care about the center of gravity. It just defines stability. And every time you see someone walking, running, cheerleaders that you guys do, that crazy things that you do, gymnastics, all of those is just basically an idea of balance. And you need to keep that balance. And the location of the center of gravity is key. Now, we haven't figured out how do we find the center of gravity of our arm. Okay, so when we have simple geometric figures like rectangles, squares, spheres, circles, etc., the center of gravity is going to be exactly the same as the geometric center. So in the case of a rectangle, well, the geometric center is going to be right here in the middle. So if this has a length of L, the center of gravity is going to be at L halves. And if this has a width of W, this is going to have a length, the center of gravity is going to be at W over 2. If you have a disk, a sphere, a circle, the center of gravity is going to be right in the center of the object. If you have a donut, and if you can imagine a donut, the geometric center of the donut is right there in the middle of the hole. So that's going to be the pivot point. That's going to be the center of mass of a donut at the center of the hole, again, outside the object. Yeah. Any questions? No? Makes sense? Okay, so let's try to calculate the center of gravity of an extended object. Sorry, let's try to find out the torque created by gravity on an extended object. So this is the rod that we've been talking about the last couple of days. So we have a rod. The pivot point is going to be at 25 centimeters. And this is 75 centimeters. And I'm going to say that the mass of this thing is 5 kilograms. Okay, so again, these 5 kilograms is distributed all over this rod. Okay, so I'm only going to have one force, and that's going to be basically the weight of the ruler of the rod of this piece of this object. Now, I'm going to assume that the center of gravity is going to be at the geometric center of this rectangle. So this is going to be 50 centimeters. Okay. Now to calculate the torque, again, the torque is the distance between the pivot point and the force that is perpendicular to the radial axis. So in this case, the distance between the pivot point and the force is this distance over here. And that's going to be 25 centimeters. Well, sorry. Yeah, 25 centimeters, 0.25 meters. And the perpendicular force, well, this is the weight. So that would be 5 times 9.8. And that's going to be the torque. And I got 12.25 newtons meter. Now, is it going to be positive or negative? Elizabeth?
Positive?
So, no, it's going to be negative. So remember, this mass or this force is going to rotate the whole object clockwise. So anything that rotates clockwise is going to be a negative torque. When it rotates counterclockwise, it's going to be positive torque. Okay? Emma? Everybody? Yeah? Okay. On the chat, makes sense? I know that was a yes. Okay. That was here or was over there? I don't know. Okay. Now we're gonna do another problem. So imagine that you have your arm. That means your arm is extended horizontally, parallel to the ground, and you're gonna be holding a dumbbell at the end with your hands. So you're gonna have your arm. I know, sorry. There you go. You get the idea. the dumbbell is going to have a mass of 5 kilograms. I'm going to call M sub D. Your arm, MA, is going to have a mass of 4 kilograms. Okay, and the length of your arm, I'm going to say that this is 70 centimeters. And I want to know what is the torque on your shoulder. Yeah, makes sense? Okay, how many forces do we have? Rihanna?
I have a question. The last one, do we need to change centimeters to meters?
Yes, we didn't? Yeah. Yeah, so instead of 25 centimeters, it's 0.25 meters. And here too, you convert centimeters into meters. Shoot. Yeah, so how many forces do we have? 2, which are? Yeah, so we have 2 masses. We have the mass of the arm and the mass of the dumbbell. Each one of those is going to create a force for gravity. So you have the forces. Each force is going to create a torque. So you need to find out the distance from the pivot point to each one of the forces. Okay? Calculate the torque, add them together, and that's it. Simple. So give it a try. How is this making sense?
Dr. Orgetta.
Yep.
I guess I'm just confused on why we didn't do this on Friday. Like, what determines the difference between the problems that we're doing now versus the problems that it was torque just equaled R F sine of theta?
So on the problems on Friday, we were ignoring the mass of the arm. That's the main difference. We were just calculating the torque caused by the dumbbell. So now we are looking at the dumbbell and the arm, and that's going to make a difference.
So that just finding the arm length is what determines that you need to find the center of gravity for it? Like, why? I'm just confused why we didn't find the center of gravity on Friday.
We didn't because we didn't have time. That was one. We didn't have time to do the center of gravity. The other thing is that eventually we're going to try to find the center of gravity of more complex structures. So with the arm, it's pretty simple. It's just at the middle of the arm. But if you have a body and you want to calculate the center of gravity of the torso and the legs and the arms, and the center of gravity of the whole body is going to be a little more complicated.
Okay, thank you.
I think I never answered your questions. She always has like, okay. Okay. So everybody got it? Ish? Okay. You got it? At all? Don't get mad at me. I'm trying.
I'm confused.
Don't get mad. I'm trying here. Okay, I'm gonna do it step by step. So we're gonna have two forces. The force of the dumbbell, there's gonna be this, which is just basically the mass of the dumbbells times gravity. And the other one is gonna be the mass of the arm. And the arm, the center of gravity of the arm is gonna be here at the center. So here we're gonna have the force of the arm, which is the mass of the arm times gravity. Okay, so the net torque is going to be the torque of the arm plus the torque of the dumbbell. Now, to calculate the torque of the arm, notice that the arm, if we only look at the torque of the arm and we ignore the dumbbell, the arm is going to try to rotate clockwise. So this is going to be a negative torque. The dumbbell, if we just look at the dumbbell by itself, it's also going to be rotating clockwise. So this is also going to be a negative torque. So these two are going to be actually negative torque. So for the arm, we're going to have negative 0.35 meters. That's this distance from the shoulder to the center of gravity, times the mass, which is 4, times 9.8. And from the dumbbell, we're going to have 0.7 times 5 times 9.8. And I get negative 48 newtons meter. That is 48.02, yes.
Oh, sorry, you lost me somewhere. Where did you get the 0.35?
So this is going to be the distance from the shoulder to where this force of the arm is placed. So it's going to be the distance between my shoulder and the force. And because we say that the center of gravity is going to be at the center of my arm, and this is 70 centimeters, so the half is going to be at 35 centimeters. Yep. Does it make sense? Okay, so now, same arm. So we're gonna have here our arm, 70 centimeters. We have the dumbbell at the end. This mass of the dumbbell is still gonna be 5 kilograms. The mass of the arm still gonna be 4 kilograms. But now we're lifting our arm, and instead of being completely straight, parallel to the ground, now we're gonna have a 30-degree angle. Now, based on your experience, if you have done dumbbells or you have picked up dumbbells or just carrying out stuff, is it gonna be harder to have your shoulder completely or your arm completely horizontal to the ground? Or is it gonna be harder to have it a little bit lift? Lift? What about if you have it down? Instead of having 30 degrees below, above horizontal, what if you have 30 degrees below horizontal? Which one is gonna have higher torque? Say that again? Higher is gonna have higher torque? Yeah. Okay. So this is the prediction. the higher your arm, you're gonna have a higher torque. Okay, so we calculated a torque of 48 newtons meters. So calculate the torque of the arm at 30 degrees above horizontal. And then we compare. No, the rotation part itself. Honestly, we're above. Be careful with the sound. You're trying to find where it's a perfect square. So you will need to draw your radial axis with direction of the force, get the frame of reference, and look at what angles you have. Really close. Is it a winter sports?
Spring
So I'm gonna do the dumbbell. So this is my pivot point. This is my arm. I'm just gonna do a line. And this is my dumbbell. And the weight of the dumbbell goes like this. Okay. Now, remember, I want the perpendicular component of this force, the perpendicular component to this axis. So I want this component over here. Okay. Now, imagine that you have this. This is 30-degree angle. This is your 30-degree angle above horizontal. This is going to be 90, and this is going to be 60, and this guy is going to be 30. So if I want the perpendicular component, so the perpendicular component of the dumbbell is going to be the weight of the dumbbell, and I can either use sine of 60 or cosine of 30. When we were talking about the definition of torque, we have an axis, and then we have a force. And then I told you, okay, we have two angles here. So we're gonna pick the one that is along the radial axis and that is less than 90 degrees. This was our phi. So in this case, we're looking at the angle that is between this radial axis and our force that is less than 90 degrees. So this will be the 60. So that's why we have the sine of 60. Okay. You will do something very similar to the arm, to the weight of the arm. So this one, you have sent. So you have your force here. And this will be 35 centimeters. Right? But if you look at the angle, the triangle, we have 30 degrees, that's 16 to 9. So you look exactly the same, just like a shorter version. And you can see that this one is actually smaller. than this one. So you know what is the force of your arm? You know what is the force of your thumb? So you're really not solving for equals to 0. You're just trying to sum these together and trying to find out what is this, what is that topic. Yeah. Yeah, cool. Okay, so for the dumbbell, we're gonna have, so the torque of the dumbbell is gonna be the radius, that's gonna be the 70 centimeters, so 0.7 meters, times the perpendicular force, which is the one that we calculate here. So that's gonna be 5 kilograms times 9.8, that's gonna be FD, that's the force of the dumbbell. And the perpendicular component is gonna be sine of 60. And again, this is gonna be negative. And the torque of the arm is very similar, but now the distance, now this is gonna be 35 centimeters. So we're gonna have 0.35 meters, 4 times 9.8, and here we're also gonna have sine of 60. Same way, we have 30, 90, 60. So this is the angle that we need. And at the end, you end up with negative 41 point, Mary, what you got?
5,
8, 5?
5, 8.
5, 8, 6. Newton. Okay, now notice how the torque is actually smaller than when you have 90-degree angle. This is not so obvious to see because usually when you're picking something like that, it's actually harder to bring it above your shoulder. But that's because there are a couple of forces that are going to be compressing towards your shoulder. But if you imagine carrying a heavy bag or your backpack and you put it next to your leg and your arm is completely perpendicular to the ground. So again, the center of gravity is below your shoulder. So the center of gravity is below your pivot point. So that's the stable position. That's the position that requires less energy to have it. And you don't have any torque. Even though you feel the pull of your bag, there's no torque. The bag is not rotating your arm. It's just pulling it down, but it's not rotating. And as you increase your arm and you start elevating your arm all the way until you reach 90 degrees, that's going to be the maximum torque that you're going to have. Okay? We're going to talk about this a little bit later, but does it make sense, this exercise, this last exercise? Yeah? Okay. Yes, Emma.
Wait, so when you go past 90 degrees, why is it not more again? Sorry.
Say that again.
When you go past 90, why is it not more again?
So this, when you have a 90-degree angle, so you have something like this, all the force of the object is rotating your arm. But when you are above 90 degrees, so now your force is going to be something like that, but now only one part is going to be rotating and the other part is going to be kind of compressing your arm. And as you increase this angle, that compressing section is going to increase. Okay. Any questions? Elizabeth? Shall we stay? Shall we go? I can do one more problem in the 3 minutes that we have. I swear.
Could you explain how you use sine of 60? Why you're using sine instead of cosine?
You can either use sine of 60 or cosine of 30. So you have 30 here. This is going to be 90. And this one over here is going to be 60, right? Now, what I need, is the perpendicular component of this force along this axis. So I need this component over here. So I'm going to redraw this. So this is my parallel axis. This is my perpendicular axis. And the force that I have is this one, FD. And this is going to be 60 degrees. So if you want this, the perpendicular component, you have two options. Either you do FD sine of 60, or you can do FD cosine of 30, which is this one over here. Yes? Kelly, make sense?
Yep, that makes sense. Thanks.
Okay. Have a good day, everybody, and see you on Wednesday. Okay, guys, see you.
I see a little sense of it.